Von was Stück. Share. Share. And then I do this. Good. So now we're going to talk about sensors. This is a little bit short. This is for you to understand how your sensors work. And again, I have said before, what we consider in this course, what we call sensors, is anything that basically anything that detects light. So it could be eyes or a camera or detectors. This is what we call sensors. But right now we're not going to talk about our eyes. So we're going to talk about the sensors that produce a digital image. So what is a good sensor? Say that we have a fluorophore, so some fluorophore that fluoresces. So a sample that fluoresces, and then the emitted light makes its way through the sensor. And so we have 3 photons that are coming here. And these 3 photons are going to be detected by the sensor, but maybe only, so when the photons come to the sensor, it could be that the sensor does not detect all the photons. And maybe it detects only 1 photon. When the sensor detects 1 photon, it's going to create a charge inside the sensor. So we can say 1 photon, 1 electron, okay? So it's a charge now. So we're transforming, if you want to say, a light information into an electrical information. And it's a 1-to-1 thing, but we do not detect everything. After that, we're going to go through some amplification steps. So the electron is going to be somehow amplified in several electrons, and so this is to amplify the signal. After that, the voltage, because this is electron, so it's a current, so we can read the voltage. So we're going to read the voltage, and then after that, this voltage is it's an analog signal, which means it's a continuous signal. So we can have a voltage that is 3.95. But in our image, we do not have 3.95. We only have discrete numbers, and they are integers. And so we're going to convert this analog signal into a digital signal with a discrete number of integers. And this is done by a little machine called the analog to digital converter. And after that, we're going to get a digital signal, and so this voltage is going to be converted into a number, which is our intensity number, and that corresponds to 1 pixel. Okay, so all this happens at 1 pixel. So either it's in a single point confocal, and each sensor corresponds to 1 pixel, or on a camera-based system, each camera pixel is going to do this job. So this is true for all detectors and cameras, all sensors. So what do we want? What would be a good sensor? A good sensor could be something that has an efficient photon detection. So it means that if we have 3 photons that come in, we would like it to feel that there's 3 photons and generate 3 electrons instead of having just 1. Another one would be we would want to have a lot of amplification so that we can detect even the very minute intensities, and we amplify them a lot, and therefore we can detect them. We would like this whole process not to be noisy. We do not want the process of amplifying and converting. We don't want it to create its own noise, and we will talk about that. And then we want the whole thing to happen very fast, clearly. So this is a super good sensor. On top of that, we also want a high digital resolution. So we spoke about that. So this is for a camera. And for a detector, the detector, if you remember, in the image, the scanner is going to record the XY information. The detectors on the point confocal only record the intensity. So the digital resolution thing has nothing to do with detectors of a single point confocal. It has to do with the scanner. However, on the camera has an array of pixels, and therefore the cameras record both the intensity and the XY. So we want, if we have a camera, we want a high digital resolution, and we also want a high dynamic range, and this we will see also later. So the good thing is that sometimes we can control some of these things. So the efficient photon detection, this is the specification of the camera. So if you already have a camera or a detector, that's it, you're stuck with whatever the specifications of this sensor is. However, everything else can be influenced by the settings. And therefore, this is what we're going to consider now. So in this lecture, we're going to talk about speed a little bit, and then about the efficiency of photon detection. And then later we will talk about the others. So the sensitivity is how many photons, incoming photons, will the sensor actually detect. And then there is a cascade of creating the electron and amplification and digitalization. This is called the quantum efficiency of the sensor. So it is the percentage of incoming photons that trigger a signal. So in here, we would have a quantum efficiency of 33%. So we have only a third of the photons that are detected. That's it, 33%. It's also often abbreviated as QE, quantum efficiency. You're going to have to find the quantum efficiency of all the sensors on your microscope. That's one of the assignments. So this is the percentage of photons that trigger a signal. And the sensitivity, the quantum efficiency, is different across the spectrum. So it depends on the wavelength. So, for example, these are examples of the quantum efficiencies. For a detector like a conventional PMT, this is the type of detectors that we have on point confocals. The peak quantum efficiency, so the highest, depending on the wavelength, the highest is going to be 35%. So 2/3 of the photons that actually make it all the way through the filters and everything to the sensor are detected. Only 1/3 is detected and 2/3 are lost. If we look at gas detectors or HIDE, we're more about 45%, but anyway, more than half of the photons are not detected. If now we look at cameras, we have different sort of architectures and different types of cameras, but you can see that the peak quantum efficiency is much higher. And the latest cameras are called back illuminated SCMOS, and they have a 95% quantum efficiency. This is really, really high. Almost all the photons are actually detected and trigger a signal. Now we can see here, these are different types of detectors. So what you find on a single point confocal. And here we have the spectrum across and you can see this is the quantum efficiency. And all these lines are different types of detectors. And you can see that the quantum efficiency is not equal everywhere across the spectrum. So, for example, this gas detector has a very high quantum efficiency, very high for a detector. So 45% around the green and yellow emission range. But then as soon as we get into the red, orange, it drops dramatically and it's unable to image in the near infrared. But then other gas detectors might be specialized for this range and they're much lower in the rest of the range. So using this quantum efficiency curve, the manufacturers of microscopes on a point confocal, they may, if you have a spectral detector, they may use, or even if you don't have actually, but if you can split the light, since we have several detectors on the point confocal, they may design the thing in such a way that normally the light, if you send the far red light or near infrared light to one detector, it's going to go to the type of detectors that work well for that wavelength. And then on the other side of the spectrum, maybe they will have a detector that is specialized in the blue. So these detectors that you have on your microscopes, they are not equivalent. So it means that you should not flip them, because then you're going to have a much dimmer signal. I can't remember who, but someone was saying that systematically the far red signal is always dim, whatever she labels and whichever fluorophore, it's always dim. It could be because she uses the wrong detector. So we'll have to figure out which detector is selected there.
Can I ask you, Sylvie?
Oh, I got scared, sorry.
Sorry, that's Sophie. I was wondering, how do these things, how do they get older? How long can you use them and assume perfect quantum efficiency?
The detectors, you mean?
Yes.
In general, the detectors are not the first thing to go. So the scanners in general start dying before the lasers as well. So the detectors are often not what goes first on the point confocal. However, the electronics can age. That does happen. And also, very often, the newer electronics is faster. So there's a lot of development in the electronics. And therefore, we have like more collection, for example, better amplification, faster system, etc. So this is quite common, but in general, it is not the case that suddenly your detector stops detecting and it's much lower than it's expected.
So you don't really do any controls for this, like
No,
let's say every year or something.
no, we don't do any control for that. So the lasers have a tendency to go down. So it would be very, very difficult to control because you would have to have like a certain environment where you can fix the excitation light as well, which is something that we do not have in a core facility in general. So
Understood.
yeah. So
Thank you.
I haven't heard in core facilities that people notice that their detector is going down in quantum efficiency. I do not know. I do not have any data about that though. So it's possible, but I haven't heard of that. But what I've heard is that definitely the lasers go down, and then everything else breaks on the microscope when it's old. So the scanners tend to go first.
But also the lamps, right?
The
Like the
lamp, that's
halogen
different,
lamps.
right? This is different. So the halogen lamp, well, yeah, halogen lamp, but also the mercury lamps, they do have a
Yes.
lifetime. LEDs have a much longer lifetime than mercury lamps, for example. But that is quite common. So we have changed the halogen lamps many times on our systems. We do not look at the fluorescence in the eyepiece, so we do not use any mercury lamps. But LEDs are quite long. They take a lot of time. But now we're talking about on the detector side. So on the detector side, I've heard detectors dying and they stop working, but not going slowly down. Now I'm no expert in that. So what you can see in here is for this blue gasp detector, we have 0% quantum efficiency at 800 nanometers. But if we look at this specialized gasp NIR, so near infrared gasp, we can see that the maximum quantum efficiency, the peak quantum efficiency, is like 20 something. And it's at this wavelength, it's 20%, so it's better. It's still crap, but it's better. And when we look at cameras, so SCMOS cameras, for example, we can see here that the quantum efficiency is very different. Now, notice that these curves are much more flat because the range is different. So we anyway have excellent quantum efficiency across the whole visible range. And also at 800 here, we would have, for example, 60% for this back illuminated SCMOS. So these are the most performant cameras these days. This is another type of camera, and they can also be back or front illuminated. And you can see in here at 800 would have 80%. So this would be a good camera if you have a long wavelength and you want to be able to image it. However, there's other drawbacks, let's say, big pixels in this one, so low digital resolution. So everything is a plus and a minus, but this is the way we look at the quantum efficiency, the efficiency of detection of photons, and that differs across the spectrum. So you will have to find the quantum efficiency curve of your detectors. Now, color cameras are a little bit different. So when we talk about detectors on point confocal, they're always black and white. When we talk about camera-based system, the cameras can be a color camera or it can be a black and white camera. What happens for, actually the chip is the same. So we have all these camera pixels, which each of them records light. And on top of that, for a color camera, we have some filters. And the filters are designed to mimic what we have in our eyes. So in our eyes, we have more green photoreceptors than blue and red. So we have about double. And so it's designed exactly the same way because the idea is to show you the colors the way human beings sort of, I mean, of course, we're all different. So the way we sort of sense the colors. So this is the reason why there are double the number of green filters compared to red and blue. This is called a biofilter, and it's stuck on the camera chip, so you cannot remove it. So this means that in the image, actually you need 4 pixels to make only 1 image pixel, right? But this 1 image pixel will contain 3 colors, RGB, green, red, and blue. So that means that when you look at the size of the pixels for a color camera, the actual size that will be transferred in the image, if you divide by the magnification, is going to be 4 times bigger. And that's because of this biofilter that we have to merge together 4 so that we get the color information inside. So this is, you can look at the quantum efficiency of these color camera, and that can be quite high as well. So we can have quite good quantum efficiency, but again, we have we have the filters, so we have to consider also for each of these pixels with the filter, even though the pixels underneath are the same, but we have a filter on top. So now this was about quantum efficiency, how many incoming photons are detected and amplified. Now we're talking about speed and what happens with speed. So in detectors, what we have in the point confocals, we scan the sample pixel by pixel, right, line by line. So it's a little bit slow. And what we have is an exposure time per pixel. It is called the pixel dwell time. So this is the number of microseconds that the laser stays on one spot and the scanner stays on one spot before the scanner moves to the next spot. That you have decided the size in between, right? You decide how big the jump is, but how long it stays, this is the pixel dwell time, and it's also called scan speed. So if you change the scan speed on your microscope, you will see somewhere the pixel dwell time. And I want you to find me this pixel dwell time. So this is one thing you will have to do, is go back to your microscope and find the pixel dwell time and take a screenshot. So let's say, for example, that we have an image where we have selected 2048 by 2048 pixels. So this is altogether more than 4 million pixels. And if we have a pixel dwell time of 4 microseconds, this is the time spent on each pixel, then we will have a frame rate, which means like how long does it take to take one image? Then we multiply 2048 by 2048 multiplied by 4, and then we convert in seconds, and this is 17 seconds per image. You can also see this in the software, how many seconds per image. If we go bi-directional, so we image, and image again, whereas if we go unidirectional, we image, then we go back to the beginning of the line, image. I remind you that in bidirectional, we can go double the speed, so we can go much faster, but we have sometimes misalignment issues, and we can correct for the alignment. There is always a tool to correct, but it's sort of, there's a limit to what it can do, let's say. So the alignment is a lot more stable, let's say, and reliable if you go unidirectional. But when you want to go fast, it's fantastic to have the bidirectional scanning. And for example, if you want to take an overview of the image, excellent to do that. So then we can go down maybe to a 0.1 image per second. And I showed them in the wrong way. So that would be 1 out of 17. And if you have a resonance scanner on your point confocal, you can go faster. So resonance scanner has a fixed speed. We cannot change the pixel dwell time because it works with resonance. We can only change how many pixels we want to select, and therefore we go faster or slower just because we collect more pixels. So resonance scanners are also excellent, but not all microscopes have them. Everybody has a normal scanner, but a resonance scanner is an option. It's quite expensive, so you have to figure out if you have a resonance scanner on your system or not. If you do not have any option to change the scanner, then you do not have one. Another way to go faster on a detector-based system, so on a single point confocal, is the fact that we have several detectors, and therefore we can image several colors at once. And that is very useful, and clearly it goes faster than imaging the colors one by one, which we mostly do on camera-based systems. So when we will talk about this a little bit later, not today, tomorrow we will talk about it. Gami will talk about it. So now we have, if we look at camera-based systems, all the pixels are exposed at the same time. So we're talking about millions of pixels as well at the same time. The exposure time can be, I wrote 10 milliseconds, but it can be smaller than 10 milliseconds. So it's extremely fast. And that's 10 milliseconds for all the pixels at the same time. So if we image 2048 by 2048 pixels, again, it's over 4 million pixels, and that leads to 100 images per second. The speed, the maximum speed we can reach on a camera-based system depends also on the readout rate. So very often in your software, if you use a camera, you will have something called readout speed, read rate, something like this. Anyway, it sounds like that. And then you can select maybe one or two or three different readout speed. And what that means is how fast the electrons are removed from the chip. So once we get some photons, and then there's this detection of electrons and the amplification step, and then we have the reading of the voltage. And this removes and it empties all the electrons to reset it before we get the next image. We have to go back to ground level, let's say. So how fast this process of removing the electrons from the chip is done, this is the readout rate. And this is before the next image is acquired. So you can see it goes in megahertz, so we can go very fast. The problem is this creates noise. If you go super fast, it creates noise. So we're going to talk about the noise also later. But this is the way to go faster, is that we can select a faster readout rate on our camera. A high readout rate creates some readout noise. And unfortunately, on a camera-based system, most of the time, we can image only one color at a time. And again, we will talk about this tomorrow. So as you can see here, we have the same number of pixels on the two systems in here, but here we have 0.1 image per second, and here we have 100 images per second with the same number of pixels. So clearly a camera-based system is very fast. And I want to say that all the camera-based systems, so it's not 100% true, let's say, depending on what you have, but if your system is a little modern, we can say that the speed limit of the how many images you can collect with a camera-based system just depends on the camera. So it doesn't depend on other things. It depends on the camera. If you have a decent computer, let's say, it will depend on the camera specifications. And but here we have several colors at once, and here we have only one color at a time. And there are some tricks. We'll talk about that tomorrow. So camera-based systems image much faster. It's not surprising. But if you use a single point confocal, try the bidirectional scanning. You will see that, for example, when you image a fast overview to navigate in your sample, this is extremely useful to use a bidirectional scanning. And then on the camera-based system, you should increase the readout rate to go faster, but this increases the noise. This is why, if you do not need to go very fast, the lowest readout rate is the default. That's what you want to use if you do need to go super fast. But if you want to go faster, then you can change the readout rate. So we will see this in a second. We will have a little speed workshop. So this is my little lecture about sensors, and I would like to know if there are any questions about this. No questions. Okay, good. So you guys will have to figure out what your all your detectors and also their specifications, pixel size, quantum efficiency, all this type of things. So now I'm going to talk about signal, background, and noise. That's an important thing.